Okay, great. All right, so first of all, I want to thank the organizers, Alex in particular, for inviting me to this workshop. I've had a lot of stimulating, very positive interactions, and I've learned a lot from all the talks. So I would very much encourage SPICE, Hira's not here, but to fund such workshops for young researchers in the future. I think this has been excellent. So the topic of this talk is bulk, that is to say three-dimensional topological superconductivity. This is an electronic phase of matter that is predicted to occur under suitable circumstances at sufficiently low temperatures. And it would be marked by the presence of a surface fluid of so-called Murano fermions. So I should say a disclaimer right at the beginning of the talk, these Murano fermions have nothing to do with the Muranos you heard earlier in the conference. These are not zero modes, there are no vortices, you cannot braid with them, you cannot do quantum computation with them. So different animal. And in fact, as Johannes pointed out earlier in the conference, there is only one so far known bona fide three-dimensional topological superfluid, which is actually not a solid state material at all, it's helium-3b. But I hope to convince you by the end of the talk that finding a solid state analog, that is finding solid state topological superconductors, is a worthwhile endeavor because we expect the physics of this Murano surface fluid to have some quite unique properties. So most of this work was done in collaboration with my postdoc Hongyi Shi and my grad student Yangzi Shou. Both of them will be on the postdoc market next year, so if their CVs come across your desk, I suggest you look at them seriously. They're both excellent researchers. So the title of the talk says something about the quantum Hall effect, so let me start with a lightning review of the quantum Hall effect. So the integer quantum Hall effect is what we would now call a type of two-dimensional topological insulator. So I have some incompressible state of matter, which has some bulk topology, which is some kind of electronic Berry phase hidden in the electronic structure. Sounds like the type of thing that would be very, very hard to measure under normal circumstances. But because it's a topological phase, on the boundary I have this gapless propagating chiral edge state. And the really wonderful thing about the integer quantum Hall effect, the reason why people like Corey are still doing experiments on it, is that it gives you a direct experimental measure of the topology. So you have this weird global property of the electronic structure in the bulk, but if you want to measure that, you just measure the Hall conductance, and it's precisely quantized in units of h over e squared. So for the purposes of the rest of the talk, it's useful to think about what distinguishes the edge state of the quantum Hall effect from, say, a normal one-dimensional system, like a carbon nanotube or a single-channel quantum wire. So if I have a single channel quantum wire, I have left and right Fermi points, I have electrons that move to the left, electrons that move to the right. But the problem is that in such a confined geometry, first of all, electron scattering is inevitable. But moreover, if I have a long wire, if I have any dirt, any junk on my wire, it's going to cause backscattering. And in particular, if I'm at very low temperatures, we know that disorder tends to have very strong effects and tends to induce Anderson localization. Now compare that to the quantum Hall effect, where the key idea is you start out with a normal one-dimensional system with left and right movers, but then you separate them with a macroscopically large bulk, which could be, say, the size of the observable universe. And then the point is that if you look only at this right-moving edge, you have right-moving electrons, they may interact with other right-moving electrons, they may encounter dirt and other junk, but all they can do is acquire a phase shift as they encounter these obstacles. There is no way for this right mover to backscatter and degrade the current unless it tunnels across the macroscopic bulk. So that's the essence of the quantum Hall effect. That's why you get this precisely quantized Hall conductance. But for the purposes of the rest of the talk, it's useful to phrase this in slightly more technical terms, which is the following. So in a normal quantum wire, charge is of course conserved. There's no superconductivity. But left and right movers are not independently conserved. In the integer quantum Hall effect, at least in the usual geometry, not the Laughlin experiment, left and right movers are independently conserved. So one can say that there is an extra U1 symmetry. And that's a general theme in topological materials, that you have some topological global aspect of the bulk, but that's reflected on the surface by an anomalous symmetry, a symmetry that would otherwise be hard to get in the lower dimensional surface theory. So now let me move on to bulk topological superconductivity. So superconductivity, of course, arises from the condensation of electronic Cooper pairs. Its hallmark is that you have resistanceless superflow of charge carried by the superfluid. I'll remind you, however, that at least in the normal case, a superfluid does not transport spin, and it never transports heat. So the only way to transport heat, say in a superconductor, is by thermally excited quasiparticles. So a topological superconductor then, and I mean a strong topological superconductor, is a fully incompressible superconducting state at the boundary of which I have a so-called Murano fermion fluid. And as I said, these are not Murano zero modes. These are deconfined around the boundary of your sample. And you should really think of them just like quasiparticles in the D-wave cuprates. So in the D-wave cuprates, you have nodal superconductivity, and so you have the coexistence of gapless quasiparticles with superfluid order. A topological superconductor is sort of the same idea, except the gapless quasiparticles are pushed out to the surface. So in particular, if you're talking about a three-dimensional topological superconductor, you have two-dimensional quasiparticles essentially running around on the surface of your sample. So topological superconductivity is not a new idea. It's been around in the guise of P plus IP, the 5-half state of the fractional quantum Hall effect. Volovik's been talking about helium-3b for many, many years. But I think the notion of topological superconductivity in solid-state materials is relatively new. And as far as I know, the first suggestion of this was in a paper by Andreas Ludwig in 2008, and shortly thereafter by Kitaev. And so the emphasis of this talk is I want to ask questions about what would you expect to measure if you had such a material in your lab? What would be the hallmarks of this surface Murano fluid? And in particular, I want to look at transport properties, and I also want to ask how stable is such a thing? Now, in terms of experimental realizations, I will have essentially nothing to say. There's a famous paper by Eresberg and Liang Fu proposing copper bismuth selenide as a potential topological superconductor. More recently, people are also looking at Dirac semimetals, Hauff-Heusler compounds, but I think the jury is still out, and that's all I have to say. So for my purposes, I'm going to say that we understand bulk topological superconductivity if I can write down some toy lattice model. So some three-dimensional Bogolubov-Dejean lattice model that you can show has these types of surface states. And so it turns out you can do that for all of the classes of 3D topological superconductors. Now, some of you may have seen this so-called periodic table of topological phases, which has this obscure Cartan classification. I don't want to get into that because it tends to confuse people. So let me just say this. Three-dimensional topological superconductors, like 3D topological insulators, are all time reversal invariant. That's the main thing you have to know. But in addition, there are actually three possible classes, and they're basically just distinguished by the amount of spin SU2 symmetry that the system would have. So copper bismuth selenide would be an example, if it is a topological superconductor, of a system with strong spin orbit coupling. So there's no spin SU2 symmetry. So that's one type of topological superconductor. But there are others, and in principle, you can have a topological superconductor with a spin U1 remnant of spin SU2. This would be something like a spin triplet P-wave topological superconductor. Or in principle, you can have a topological superconductor with full spin SU2 symmetry. And in fact, in a lot of the talk, I will use this class as the example, although we give results for all classes, just because this one is, in a way, the most complicated. So now I want to step back and say, let's assume we have a perfect sample of a bulk topological superconductor and ask, what do the surface states look like? And the answer is that superficially, they look a lot like graphene. So you have massless relativistic quasiparticles running around on the surface of your sample. So I can write down a Hamiltonian. This is in the absence of disorder, the absence of interactions. I have some Dirac or Murano spinner. If I'm talking about a case where spin is conserved, I can actually write it down in terms of a complex spinner. In class D3, where there's no conserved spin, then this is necessarily real. That's a technical detail. So the point is that the Hamiltonian for my surface fluid just looks like this. It looks like graphene, but I'm hiding one detail, which is that there's an additional index on the psi, which is a valley index, or I'm going to call it a color index. And the way this works, at least for these simple models that we can write down, is that the number of colors, the number of species of Murano fermions that you get at your surface is just equal to the modulus of the bulk winding number. So, yeah, question? Okay. So there's an additional index here which runs from 1 to the modulus of the winding number. So especially if you're an experimentalist, you see this Hamiltonian and you should immediately ask the question, well, why should I care about this? I mean, there are many platforms now for Dirac fermions. Arguably, graphene is the easiest to work with. And here I'm talking about materials which we're not even sure exist yet. And my argument is that these particular types of Dirac fluids are very special because of the way time reversal is implemented. Because remember I said the hallmark of a topological phase is that you have topology in the bulk and some local anomalous symmetry on the surface. So for the surface fluid of a topological superconductor, that translates to an anomalous form of time reversal symmetry. And that's where all the interesting physics comes from. And so, again, skipping technical details, it turns out that if I choose a certain basis such that my surface fluid looks like this, where I have some kinetic term, this sigma acts in some space that you need microscopics to understand. It's some combination of particle hole space and orbital space. And of course, I have this additional color space. Then it turns out that you can write time reversal as this chiral condition. So time reversal is just the fact that this thing anti-commutes with the third Pauli matrix. Now, that may look very strange to you. First of all, this doesn't look anything like what you normally consider time reversal. There's no complex conjugation. And moreover, this looks like something that's very basis dependent. So again, I don't want to get into details, but let me just say two things. One, anytime you have a quasi-particle system, like a Bogoliubov-de Gennes Hamiltonian, you can always write time reversal as a chiral condition. It has nothing to do with topology. It's just a simple fact. Second, it's true that the form that this takes is basis dependent, but the claim is that once I choose this basis, this form is unique. That's not obvious. It was proved in an obscure mathematical physics paper by Bernard and Leclerc back in 2002. So mathematical physicists can do useful things sometimes. So let's try to get some intuition as to what would make the physics different on the surface of a topological superconductor. And one way to do that is to ask, well, what if I start perturbing the surface? What types of objects, currents, or densities that could couple to, say, disorder or external electric fields, other types of perturbations, are time reversal allowed, and which ones are time reversal odd? And so just like in other systems, if spin SU2 is a good symmetry, which is the case for two of the classes, or at least a remnant of it is a good symmetry for two of the classes, then I can have spin currents. Those are time reversal even. The spin densities, of course, are time reversal odd. But I can also have valley currents. And it turns out the valley currents are also time reversal even objects. And in general, I can have more than one valley. So the helium-3 case is a special case where you have only a single valley. That's winding number 1. But most of this talk, I'm interested in 2 or more valleys. And in particular, for this class C1, you actually have to have an even number of valleys. So in general, this is going to be a set of non-abelian currents that connect the different species of your Murano surface fermions. But then everything else turns out to be time reversal odd. So any type of valley density, if I try to polarize my valleys, I always get something that breaks time reversal. And any type of mass term that you would write down that would open up a gap is also time reversal odd. But physically, that makes sense. You expect that in a topological phase, I shouldn't be able to open up a gap without breaking time reversal. So another interesting question you can ask is, well, how should I interpret these mass terms? So for example, there's a mass term you can always write down that's invariant under, say, spin SU2 and valley symmetry. So what is this thing? So if you think about a topological insulator like bismuth selenide, we know that if, say, I have a surface in the xy plane, and this is the z direction, if I apply a magnetic field in the z direction, that Zeeman coupling will open up a gap on the surface Dirac point for the surface fluid living on this surface. But that's not true for a topological superconductor. For a topological superconductor, the Zeeman field couples to the spin density, which actually just, it's like a potential coupling. So how should I think about this mass term? Well, this is a bit theoretical, but one way to think about it is actually imagine turning on strong attractive interactions on the surface of your topological superconductor. That might be hard to do experimentally, although we'll see that disorder can help later in the talk if I get to it. But in principle, I can imagine turning on very strong attractive interactions on the surface such that I induce surface superconductivity. That can gap out the surface, just like in an ordinary topological insulator. But the difference is that here it breaks time reversal symmetry. So this mass term is most naturally interpreted as some kind of surface superconducting order. And associated with it, it's a time reversal braking surface superconducting order, and associated with it is some kind of quantum Hall effect. Just like at the surface of a 3D TI, you have the half-integer quantum Hall effect, but I'm not going to talk about this. Okay, so one final slide of setup. So the first thing I want to do is I want to start asking, what does disorder do to such a surface Murano fluid? But I've just told you that the only way you can couple to this fluid in the absence of time reversal braking perturbations is by coupling to currents. And so in particular, if I have a surface Murano fluid that's spin SU2 symmetric, or I don't have magnetic impurities or spin orbit coupling, the only thing I can couple to are these valley currents that connect the different valleys. So that already suggests that this is going to be a very different arena than graphene. If you put disorder down on graphene, you can couple to mass terms, you can couple to vector potentials, you can couple to scalar potentials. This surface Murano fluid only couples to these vector potentials. And so if you want some kind of cartoon picture of what disorder does on the surface of a 3D topological superconductor, it's something like quenched quantum chromodynamics. You have multiple species of massless quarks, which are running around, and they're scattering off of some kind of frozen sea of gluons encoded in this non-abelian gauge potential. So now let's try to understand transport in such a system. And so this is the only derivation I'm going to go through. It's very simple, doesn't use any complicated tools, and it's not mine. But I think it's very illustrative. So where we have a two-dimensional surface that's very, very different from the edge of the quantum Hall effect. You know, in the quantum Hall effect, you have right movers, they can't backscatter, they can only go forward. But when you're in 2 dimensions, you certainly can scatter off of impurities. Even if you suppress perfect backscattering, you can scatter at some finite angle. So you would expect disorder might have some effect. And in particular, we know that in 2 dimensions, when you have a lot of disorder, it tends to cause, again, Anderson localization. Weak localization, maybe weak anti-localization. So we want to look at quantum interference corrections to transport. And in particular, I'm going to start out by talking about spin transport because that's a bit easier. So I'm going to think about either class C1 or class A3 where there's at least a U1 remnant of spin SU2 symmetry, and I'm going to calculate just the Coupeau conductance for that spin transport. Then I'll talk about thermal transport after that. So here we go. Well, if we want to calculate a conductivity in a non-interacting system, it's really simple. You write down the Coupeau formula. So here it is. If you're a theorist, at least, you've seen this before. There's an advanced Green's function. There's a retarded Green's function. We usually represent that as a single Feynman diagram, a bubble. Here's my advanced Green's function. Here's the retarded one. And sitting at the vertices are some current operators. So these are just Pauli matrices. And this alpha is 1 or 2, depending on the x or y directions. Okay? So this looks like the simplest quantum field theory calculation ever. It's one Feynman diagram. But of course, life is not so simple, because the way I've written this, these are Green's functions defined in a fixed realization of disorder. So if you were to try to literally calculate this, you would have to invert this differential operator, which depends explicitly on the disorder potential. And of course, we have no idea how to do that. So normally, this is a very complicated problem. You have to find some way of averaging over disorder. Then you calculate self-energy corrections. Then you calculate vertex corrections. That gives you the classical conductivity. Then you calculate cross diagrams. That gives you the first quantum interference correction, and so on. So it becomes a whole world unto itself of diagrammatics. Here we don't have to do any of that. Yes? No, it is not real spin. It is, well, so it actually depends on the class. So in most of the talk, I'm using class C1 as an illustration, and that's a case where you have spin SU2 symmetry. So in that case, the pseudospin is some combination of sublattice and particle hole degrees of freedom. You need a microscopic model to pin it down. It's precise in the bulk, but you always have this phenomena that when you go to the surface of a topological phase, you sort of lose half the number of degrees of freedom. So it's some projection of those degrees of freedom. In class D3, where you have strong spin orbit coupling, they can be literally the spin Pauli matrices, although it might depend on the surface you're looking at. So yeah, here, no. No, good question. So this is still pseudospin. This is still pseudospin, but what I've done, so I'm calculating the spin current, and I've hidden the spin symmetry. So I'm thinking of this as a complex Dirac fermion. The U1 charge is actually the charge associated with rotations about some spin axis. So it looks just like an electrical conductivity. So this is still a pseudospin matrix. Real physical spin is conserved, but hidden. Okay? So how do we evaluate this? Well, we can do it very simply without doing any diagrammatics, and we use two facts. First of all is this weird form of time reversal symmetry. So we used this before to figure out which types of invariants are allowed if I start turning on perturbations, but you can also use it to change advanced Green's functions into retarded Green's functions. So you can just check that if I conjugate with this third Pauli matrix, put in a minus sign, I turn an advanced Green's function into a retarded one with minus the energy argument. And so what that means is I can take this usual term of advanced and retarded Green's functions and make it look like this funny anomalous term, which we usually ignore, that has only two retarded Green's functions. And all of these guys sit at zero energy because I'm calculating the DC zero temperature conductance. No, I've already performed that Matsubara frequency summation. No. So I mean, if you wish, I could write this formula is exact. This is what you would get from Keldysh if you wish. I mean, so the full form, if I had written out the full form at finite temperature, there would also be a df d epsilon. And it involves retarded and advanced Green's functions times the derivative of a Fermi step. It's just the Kubo formula. Right, no. Okay. Yeah, but we summed over the internal frequency. The internal, look, if I'm doing imaginary time, right, I have this bubble. And there is a Matsubara summation. So these are both imaginary time guys, right? I have a single Matsubara summation to do. I do that summation using some contour trick, and that translates into some Fermi functions. Then I take frequency to zero first, then the Fermi functions become a derivative, and then I take temperature to zero, and that just becomes a delta function that puts all these Green's functions at zero. But that analytic continuation turns the imaginary Green's functions into retarded and advanced. So this is exact. It's the vicinity of the Murano point, if you wish. This is just, you would write exactly this formula in graphene. This is exactly the same formula you would write to calculate the Kubo conductivity in graphene, but you can't evaluate it so easily because you don't have this funny form of time reversal symmetry. You would have to actually disorder average and blah, blah, blah. Well, just wait. So again, this is not my argument. This is in the literature, so I don't want to spend a huge amount of time on it. I'm just trying to give a short explanation. But the point is that normally you would average over disorder. And so you would have to calculate self-energy corrections and vertex corrections. And even then, that would only give you the classical conductivity. Then if you wanted to calculate actual quantum interference, which is what I'm interested in, you would have to go further. What I'm saying is that I don't have to do any of that. So I'm just sticking with this exact representation of the Kubo formula. And now I exploit this funny form of time reversal, which lets me get rid of this thing that has advanced and retarded Green's functions. This is what we usually think of as the Kubo formula. But I can actually write it and make it look just like this anomalous term that has only two retarded Green's functions. And one slight thing that happens is because I stick in the sigma 3, if I was initially looking at, say, the XX conductivity, it changes this term, so now I'm looking at the YY conductivity. So now I get a sum over X and Y. So I can make this term look like this term, and now if you've spent some time doing transport calculations, you should immediately scratch your head and think, well, this looks like it should be zero, either by gauge invariance or by causality. But it's not quite true. Yeah. Yeah. So exactly. So again, whenever you have a quasi-particle system, it turns out you can write time reversal as a chiral condition because a quasi-particle Hamiltonian, at least at the first quantized level, is automatically particle symmetric, right? If you write it in terms of a Nambu spinner. So combine that with time reversal, which is some conjugating condition, you always can write it this way. So if I could even study a normal metal. In principle, I could encode it in this way. And I could take this term and write it in terms of two retarded Green's functions. So that's actually not special by itself. What's special is the final step, which is noticing that when I make this term look like this term, the thing I still have sitting here is just a current operator, not a current operator times something else, not some other operator. That's crucial, because the final step is to use the Ward identity. So for non-interacting particles, the Ward identity says if I have two Green's functions of the same type being integrated over this common argument at the same energy, then I can replace this, and with a current operator sitting in the middle, I can replace this with a single Green's function, multiplied by the difference of the first and last arguments. Now, in the form I have here, I've got to be a little bit careful because notice I get the difference of this first argument and this last argument, but here the first and last arguments are the same. So that has to be regularized somehow. But fine, I can choose some kind of regularization, and you can already sort of get the sense of where the physics is going, right? So what we've done is we've reduced the conductivity in some complicated disordered medium to the short distance behavior of a single retarded Green's function. But the single retarded Green's function just satisfies some very simple condition at short distances. Namely, it's got to give you a delta function. Another physical way to think about this is that the conductivity is coming from the short distance behavior of the Green's function. If I've got impurities, let me just look on scales shorter than the elastic scattering length. Then I should be able to evaluate this using the clean limit. And if you do that carefully, what you get is a universal number, which is 1/8 pi squared. And in addition, there's a factor of the modulus of the winding number because of the trace. So every species gives me 1/8 pi squared. And this is, if you wish, a manifestation of the 2 + 0D chiral anomaly. So like I said, this is not our work. This has been known for a very long time. A slightly more technical version of this argument appears in this paper by Andreas et al. In '94. Cvelek did it for the non-abelian case. The argument I just gave you is from this paper by Ostrowski, Gornier, and Merlin in 2006. But the conclusion is always the same. The conductivity is completely independent of disorder. And so if you could find a topological superconductor and you allow for disorder on the surface, the claim is that in the case of spin conductivity, it would be completely independent of that and would only reflect the bulk winding number. Yes? AC conductivity is much harder. AC conductivity will depend on disorder, and yeah, so then you have to actually do something. Also, it turns out we can also get the thermal conductivity. So for these cases where you have conserved spin, we can do it with Wiedemann-Franz. And even in class D3 where you don't have conserved spin, it turns out you can still use Wiedemann-Franz by basically doubling the system. You get some fake U1 symmetry and you use Wiedemann-Franz. Yes? Yes, absolutely. So what is special is this funny form of time reversal. Now, like I said before, whenever you have a quasi-particle system, you can write time reversal in a way that's similar to this. But what's crucial is that whatever this matrix is, just interchanges the current operators. That's what's special. That's what Bernard and Leclerc showed back in 2002, that there was some funny Dirac Hamiltonians way before anybody knew anything about topology. So we had these funny Hamiltonians, we had no idea what they were useful for. But they noted that there are these funny Dirac models in 2D that have this property. Yeah, this is the crucial ingredient. Right. Well, so first of all, I'm only talking about zero temperature. So I'm not talking about, there will be inelastic corrections at finite temperature. But second, yeah, so I mean, even in that case, if you take the idealized model, it does predict E²/h. So something is going on there where, maybe you have puddles or, so. So, okay, but I can give you an example where this is actually measured. And an example of where it's measured, so this conductivity has already been seen in experiments, but in a very different guise where it's actually not protected, which is take a very small piece of graphene, dope to the Dirac point, and measure the Landauer conductance. That's exactly what this is. It's just the Landauer conductance in graphene. The difference here is that the claim is that it's robust to the effects of impurities as well. And that's special. That's certainly not true in graphene. Yeah, this is I have given this derivation in a fixed realization of disorder. So yeah, so that becomes a delicate question. So this is again the issue of what is the conductivity of graphene at zero temperature doped exactly to the Dirac point. And if with no impurities, that's a delicate question. So in the right mesoscopic setup, it is this conductivity. But if you're at any finite temperature and you don't have impurities, in that case, of course, the conductivity is infinite. So it's a funny vanishing of it's the fact that the density of states is vanishing, and yet there's no disorder, and out comes this finite conductance or conductivity. I'm in 2D. Right, but that's some approximate treatment. I have not used any approximations here. Now, look, things could go wrong. For example, if I introduce disorder that introduces energy scales that mixes into the bulk, then certainly this result is not going to hold, because this is a result that only works for the low energy continuum theory of the surface. So this is, if you wish, a result for weak disorder. Yes. Yes, but in a D-wave superconductor, this calculation doesn't help you, because the point is that you have this formula, spin SU2 is conserved, you can talk about spin conductance, you have a chiral form of time reversal, but this matrix does not just interchange the currents. It does something else. So while you can write your conductance this way, now you have to do something else. You can't just use just use the Ward identity. So that's what I'm trying to say, is that there's something very special with this system where the time reversal just interchanges the currents, and that's why you get this result. You do not get it in the D-wave Couperts. D-wave Couperts, you actually expect to have localizing corrections to transport. And that's been shown with sigma models and other tools, numerics. So, but again, none of this is my work. This is just, all of these results are in the literature. So let me try to get to what we actually did. Yes. Yes. No, well, you mean, okay, in the course of this calculation, yes, yes. Effectively, yes. For that term that I'm replacing, yes. It's strange, yes, but again, there are many papers claiming this, So what we wanted to do was to see how robust this result is. So if you're familiar with quantum corrections to transport, there are actually two types that you have in 2 dimensions, well, in any number of dimensions. So you have scattering off of impurities, but if in addition you have interactions, then if you have a normal 2-dimensional electron gas, you put down a bunch of impurities, you know that those impurities are going to cause Friedel oscillations in the density. And so in a real interacting disordered system, which is what you always have in the lab, when your electrons are moving through your 2-dimensional electron gas, they scatter not just off of the impurities, but also off of the Friedel oscillations. Those are called Altshuler-Aronov corrections, and they can be as important or more important than these pure quantum interference corrections. So we wanted to calculate Altshuler-Aronov corrections. Now again, in the normal life, as Igor Leiner would say, you would use some diffusive metal where you would average over disorder and draw diagrams using diffusons and couperons and this type of thing. But there's another approach which is more useful for us here. So again, let's just write down interaction corrections to the conductance order by order in the interactions, but using the exact Green's functions for the non-interacting problem. So again, I assume that I can somehow compute these retarded and advanced Green's functions using in a fixed realization of disorder. And my claim is that all of these corrections vanish. Now, that derivation is more complicated than the one I gave on the previous slide, and considering how much trouble I had with that one, I'm certainly not going to explain this one here. But it uses only two ingredients. Again, time reversal symmetry and the Ward identity. That's it. And to get some feeling for how this works, the basic idea is that if you want to think about a conductance correction, think about a free energy correction. So that's some bubble or maybe a bunch of bubbles. It turns out the only ones that are important are when two current operators are in the same bubble. And so the idea is that you have some bubble, and it's dressed by all sorts of interaction lines. Take two current operators and insert them. That's a conductance correction. But it's quantum mechanics. You have to sum over all the corrections. So that means all possible places of putting these current operators in. So you do that, say holding one of them fixed. You use this guy to change all of the advanced Green's functions into retarded ones. And then you use this to basically contract everywhere you insert this second current operator. And then when you sum around all the insertions, it's basically you're summing around the circle of these differences and they cancel. So that's a very crude sketch of how this works. We have explicitly checked this through two loops, just using these two rules. So you can find that. Yeah. So another, yeah, exactly. Yeah, it's not completely trivial because now you have energy exchange and you have to account for that, but it can be dealt with. Yes, I mean that's the essential idea, and it's only actually the zeroth order term, which is the one that is non-zero and gives you this funny finite value. Yes, yeah. So you're always automatic. This is another nice thing about topological superconductors, if we can find them, which is that, in a TI, your Dirac point is maybe near the conduction band, maybe near the valence band. It's somewhere random determined by the materials, and also your doping level is somewhere random. In a topological superconductor, just because of the natural particle-hole symmetry you have, first of all, the Dirac point sits right at the chemical potential, and that's guaranteed to be below the bulk gap. So the superconductivity aligns all of these things. So the system automatically always sits right at the Dirac point. But there's also a very simple hand-waving explanation for why we find no Altshuler-Aronov corrections. And that's simply the fact that there is no density, either potential or mass density, that can ripple. Because if such a thing were even to become non-zero, forget about showing Friedel oscillations, it would break time reversal symmetry. So therefore, there are no Altshuler-Aronov corrections to any order, and we expect that at least the spin conductivity is truly universal. And then if Wiedemann and Franz still holds, which we have not shown in this language, so it would be great if somebody did a full calculation of the thermal conductivity using these tools, but it's formidable, we haven't tried it. But if Wiedemann and Franz holds, then this result holds as well. Yes? There are no Friedel oscillations. No, because in graphene, well, so that's a slightly complicated question. So in graphene, if you put, say, strong enough impurities, even at the Dirac point, you get some density variation. Yes, you would, absolutely, absolutely. No, here you do not have them. You do not have them because, so I mean, for example, a type of impurity in graphene that would definitely give you a Friedel oscillation is, say, locally I put a staggered potential. So that's a mass term in graphene, and that will definitely give you oscillations in the charge density and in valley density. Here, they're disallowed by time reversal. So, okay, so. Right, so that's exactly the question. So charge density is not really well defined for this because it's a quasi-particle fluid. If you insist on asking where is charge density as a fermion bilinear, in these models at least where we can map it to a microscopic lattice model, the charge density actually appears as a component of the valley current, a diagonal component of the valley current. It can't appear as anything else because it has to be time reversal symmetric, obviously. So what I'm saying is that certainly that, so charge density, like if I put down charge impurities, is allowed, but it can only enter in the guise of this intervalley scattering, this vector potential. So what I'm saying is that if the usual picture of Altshuler-Aharonov corrections goes through, then you need some conserved density to ripple. So say the spin density, or a valley density, or a mass density, or something like this. But none of those can happen here because of time reversal symmetry. Yes.
Is that important for anything or not?
It's not important for anything because where it shows up is here. It shows up as a type of scattering that must take the form of a vector potential. You can show this explicitly, starting from a microscopic bulk model. If you ask what bilinear in the surface theory corresponds to charge density, it's actually a component of the valley current. So yes, this is inhomogeneous. It's a type of disorder, but we already know from this previous derivation that that does not affect transport. It does have other effects, which I'm probably not going to get to, but okay, so maybe I should skip through. So there's a second version of this. So you know, maybe you're saying, well, you know, this seems simple enough. I'm using only 2 ingredients. But maybe there's some problem. I'm expanding perturbatively in the interactions. And also, these Green's functions are rather formal objects. They're objects defined in a fixed realization disorder. These wave functions are delocalized. And in fact, they actually have very intricate multifractal statistics. So you might worry that somehow something is going wrong in these formal manipulations. So it turns out there's a completely different way of approaching this problem, which, again, I think I should skip because I want to get to a little bit more physics. But long story short, you can use non-abelian bosonization to cook up a sigma model description of this system. And yeah, let me skip the details. The sigma model ends up looking just like the so-called interacting sigma model that was invented to describe diffusive interacting metals, but we derive it with completely different technology using non-abelian bosonization. And it differs from the usual type of sigma model because of this Wess-Amino term. And there's also some technology which allows us to get a perturbative expansion in this language. So it turns out that when the winding number is large, the coupling of the sigma model is small. And so you can actually just do perturbative RG with this complicated matrix sigma model. There's a deep reason for that coming from the fact that if you start out with a clean Dirac theory and you add this very special type of disorder, the system, the description of the wave functions exhibits something like non-abelian spin charge separation. It's something called a conformal embedding. So this is something that only works for this, again, this very special type of disorder and allows us to get this type of sigma model. So long story short, you can do perturbative RG. And if I tune this parameter away from its native value, which is 1/k, I do get corrections. I get weak localization corrections, weak anti-localization corrections, and Altshuler-Aharonov corrections. So this is the leading corrections to essentially the resistance, either spin resistance or thermal resistance in this description of these surface states. But if I set lambda equal to 1/k, all of these corrections vanish. So it's a completely different way of approaching the problem, but it gives the same answer to lowest order in a large winding number expansion. So, okay. In the last 15 minutes, I want to talk about some other physics related to the disorder. So it seems like disorder has no effects whatsoever. It does not affect transport. It does not create Altshuler-Aharonov corrections. There are no Friedel oscillations. The density of this Murano fluid should be perfectly uniform. And so you would say, okay, we can just forget about disorder. This is just like the quantum Hall effect. Not so fast. So we know that if I have a normal 2-dimensional electron gas and I turn on strong disorder, or well, let's say intermediate disorder, I can localize all my single particle wave functions. So what I'm plotting here is the probability of 4 wave functions with nearby energies in a normal situation. So these are strongly localized states. So what do the wave functions look like on the surface of a topological superconductor? Are they perfect plane waves? The answer is no. They're highly inhomogeneous. They're strongly affected by disorder. They're critically delocalized, just like the wave functions at the plateau transition in the integer quantum Hall effect. So what I'm plotting here is, again, the probability of 4 different wave functions shown in different colors. The reason I'm plotting 4 of them will become clear in a couple of minutes. But the main point is just to notice that these wave functions are highly rarefied. They're very inhomogeneous with sort of these rare peaks. This was numerics done by my graduate student. And so the same types of states are seen at the plateau transition in the integer quantum Hall effect. So the integer quantum Hall fluid is usually a topological insulator, but when you go from one plateau to the next, you go through a bulk topological transition. That means you have to have a bulk quantum critical point. At that quantum critical point, you have conductance through the bulk, and the wave functions look like this in the presence of disorder. They're highly rarefied, and they have interesting statistics. And technically, the way that we understand these wave functions is the following. So if I take such a so-called multifractal wave function, the idea is to look at a level set of the wave function. So set the probability amplitude equal to some value, but let that value scale with the system size with some exponent alpha. Then you look at all the points where the probability equals that value, and you calculate the fractal measure of that set of the sample. So that gives some fractal measure f of alpha. And then by knowing how f of alpha behaves as a function of alpha, you get a set of statistics used to characterize this complicated object. So this is something called multifractal analysis. It was invented by Mandelbrot to try to understand turbulence. It's used in financial markets and other types of complex phenomena. But the great thing about multifractality in critical Anderson delocalization is that these statistics are universal, which is really strange if you think about it. So in ordinary quantum critical phenomena, you have a handful of independent universal exponents and everything else can be determined by scaling. When you're sitting at an Anderson metal insulator transition, at least a non-interacting one, you actually have a continuum of independent fractal dimensions. That's this f of alpha curve plotted as a function of alpha. And this has been most investigated in the case of the integer quantum Hall effect. The point is that you can use different microscopic models to do the calculation. You can use a real space Hamiltonian type binding model. The most sophisticated calculations are done using the network model. All of them give the same universal curve. So that means even though an individual wave function looks completely random and rarefied, the statistics can actually be computed. Well, the statistics turn out to be universal, and that means you have some hope of computing them. And so let me skip this. The only point I want to mention is that for all of these topological superconductors, we can actually compute these statistics using the so-called conformal embedding theory. And so you get some exact expression for f of alpha, which depends on some parameter. So CFT gives simple predictions. We can check those numerically, and it works. But now, the main point. OK, so we have these wave functions. The wave functions are critically delocalized, governed by some universal statistics. So what? Why should I care about this? It sounds like some exotica that only somebody who does Anderson localization for a living would be interested in. Well, the point is that when you have disorder and you have interactions, this rarefication can become very important. And so that was pointed out recently by a bunch of works by Feigelman and collaborators where they've been studying the superconductor insulator transition, taking into account the multifractal structure of wave functions near the transition. So for us, what we're going to ask is whether interactions are really irrelevant or relevant if I turn them on in the presence of disorder for this Murano surface fluid. And so one way to, so there's an additional ingredient, which I think is not that well known outside of the Anderson localization community, which is really quite amazing, and that's something called Chalker scaling. So the idea is the following. So remember, before I showed you this plot of 4 different wave functions. There's a reason I'm showing you 4 of them and not just one of them. So if you look at this plot, if you look at a given wave function like the green one, it's very random, very spiky. But if you look at some of the other wave functions, they're also very random, very spiky, but you notice that the spikes tend to cluster. There's a deep reason for that. That's Chalker scaling. That's something John Chalker pointed out in the context of the quantum Hall effect way back in the 90s. Mathematically, you can encode it in the following way. Take a critical wave function at some energy, take its probability, multiply it by the probability of a wave function at some higher energy. And then what Chalker scaling tells you is that as you scale energy, this scales as a power law. But if you think about it, that can only happen when your wave function is a bunch of rare peaks. That can only happen because nearby wave functions have the same rare peak structure and sort of nest like Russian dolls. So this is a deep reason for why the scaling theory of localization actually works, which is not a priori obvious at all. So scaling theory tells you that when you have a disordered, say, three-dimensional system, you have some localized states, you have extended states, and in between them you have a mobility edge. But that's not the most obvious answer that you might have guessed. You might have guessed that you would have extended states and localized states interwoven in some random fashion. But Chalker scaling tells you that no, actually, all of these wave functions that are critically delocalized, like you're sitting at a metal insider transition, have this correlated structure of peaks. So that's why scaling theory works, but also what it means is that disorder can enhance interactions. Because say if I have short-range interactions, like I would have at the surface of a topological superconductor, any long-range interactions are screened by the bulk condensate, then the fact that these wave functions sit on top of each other means that I can strongly enhance short-range interactions. So what we want to do is we want to use the matrix elements in these rarefied states and see, are interactions still relevant? Are we topologically protected or not? And so again, I think I'll skip the details. Basically what we do is we write down all of the short-range interactions allowed by symmetry. There's again two ways to do the calculation. One is to use scaling and use dimensions that we extract from the conformal field theory. Another way of doing it is by going back to our Finkelstein model, which we can use in the large winding number limit. These give results that are complementary. The CFT can give us the scaling dimensions for any winding number. The sigma model only gives us correct scaling dimensions for large winding numbers, but it can also give us nonlinear corrections. So we can see if something is unstable, is there some non-trivial fixed point or something like this. And so long story short, what we find is something that is actually initially surprising. So in one of the three classes of topological superconductors, we actually predict that the surface states are not, in fact, stable. So the story I told you before about transport, that's only true if you have these stable surface states to sufficiently low temperatures. But for one of the three classes, that's actually not true. And so we can draw the following phase diagram. So here is my clean, ideal Murano surface fluid. If I turn on generic short-range interactions, they're irrelevant because I have a Dirac dispersion, vanishing density of states. Okay, no problem. Now, if I turn off interactions, turn on disorder, disorder is always a relevant perturbation, and it flows me to this conformal field theory, which is really a description of the statistics of the wave functions. So what we've done is now look at the stability of this point. And for this class, it turns out for any winding number, so this is a class where you have spin SU2 symmetry, you actually flow away. So the CFT says you always flow away, and the Finkelstein model says there's no non-trivial fixed points. And actually, the dominant instability seems to be towards surface superconducting order. And again, the physics here is not really unique to a topological system. It's just this fact that you have these nested multifractal wave functions that enhance matrix elements. And that type of physics comes up in the superconductor insulator transition. It also comes up in the physics of the Anderson-Mott transition, if you dig back into the old review by Belitz and Kirkpatrick. So again, let me skip lots of details. Long story short, if you look at the other two universality classes, it turns out you can have stable surface states. So this problem only occurs in one of the three classes. So particularly in class D3, where you have spin-orbit coupling, that would be the copper bismuth selenide story, although copper bismuth selenide, it would again give you only one Murano species, so then none of this is really important, and you get a quantized thermal conductivity for free. But actually, for any winding number, we've been able to show that weak interactions don't do anything. They're irrelevant. In this class A3, which is sort of a marginal case, either the interactions are irrelevant or it turns out as a function of some additional disorder parameter, you can have some new critical fixed point. But the main takeaway is just that for these other classes, including class D3, which is probably the easiest one to realize experimentally, this problem doesn't happen. So that's the talk. So the main takeaways are that we predict universal transport coefficients, spin and or thermal conductivities at the surface of a topological superconductor so long as the surface remains stable. But in one of the three classes, actually the surface states are never stable in the presence of disorder and interactions. And so let me just close with a few open questions. So actually there are a lot of them. One of them would be an honest calculation in the Dirac language of the thermal conductivity. So this is probably the most exotic. So These results suggest that the surface states of bulk topological superconductors are a lot like the integer quantum Hall effect. But I don't have any more deep explanation of that. All I can tell you is that the surface transport is quantized. Now, does that mean, is there something like a TKNN formula for topological superconductors? It doesn't seem easy to do that because conductivity and conductance have different units in 3 dimensions. But who knows? And maybe the most exotic scenario would be, is there a fractional analog? So there's been a lot of work on strong interactions on the surfaces of topological phases, topological insulators, topological superconductors by Lucas Wadowski and others. And what they find when they turn on very strong interactions is that they can create gapped phases at the surface that are analogs of the fractional quantum Hall effect. But since here we have something like an integer quantum Hall effect with gapless surface states that have quantized, integer quantized transport coefficients, it raises the question, I mean, I have no idea, is there a fractional analog? Meaning some kind of weird bulk topological order, I don't know, you're braiding strings of anyons or something, but with a gapless surface that has fractionally quantized transport coefficients. And another open question is, what about so-called weak topological superconductors where you have gapless degrees of freedom in the bulk? Okay. That's it. Yes. The thermal conductivity? The thermal current operator. Well, it looks like the component of the stress tensor for a Dirac fermion. So it has a polymatrix and a derivative. Yeah, so that I don't know. So the tunneling density of states is affected by disorder, and you get some universal exponent. So in principle, if you, it could very well be affected by interaction. So usually Altshuler-Ernov corrections effectively affect conductance through the density of states. That's clearly not what's going on here. So no, I think there will. Right. Yeah, we're calculating Dc conductivity. Absolutely. Yes. Yes. So that's a good question. Yes. But it appears in 2 very different languages. So when we're calculating here with just diagrams, what are we really doing? We're writing down generic short-range interactions. Actually, we write down generic short-range interactions that are invariant under Valley symmetry, but we expect that that's not important. But we just do that to simplify our lives. So actually, you can ask, what types of short-range interactions can you have? And so usually in disordered system, the interactions that are important are ones that correspond to some preserved symmetry, like time reversal or spin SU2, say. So actually in class D3, for example, the only type of interaction you can have is in fact a Cooper interaction. But at the level, when you're working with these Dirac fermions, they just look like a bunch of short-range interactions. There's no notion of a pairing instability unless you were to make the interactions very strong without disorder. Yeah. No, you can. You can. There's no problem. And in fact, we know that because one of the ways we know that is that like I said, there is an interaction here that corresponds to a Cooper instability. And we can calculate its dimension using conformal field theory. We can then go to the corresponding sigma model. The sigma model has a Cooper channel. And we can calculate the beta function for this, and they match. So we have 2 completely different technologies that tell us that we're looking at the same type of interaction, and we do include Altshuler-Ernov corrections from that channel in both technologies. So the easiest way to think about this is actually in the sigma model language. So the point is that normally you would have corrections to transport coefficients. So that's a parameter in your sigma model. But you also have corrections to the interaction beta functions. So it turns out that all of the corrections to the transport coefficient vanish. But you can still have an instability if the interactions themselves get enhanced. That's what I'm talking about. Yes. Yes. Okay. They should be 0, exactly. Yes. No fluctuations. So that's what I say. It looks a lot like the quantum Hall effect, but I don't have any deeper explanation. What I would really like is some kind of deep topological field theory argument that explains why this is so. But all of the work that's been done so far on relating on topological field theory and topological superconductors only considers the case where you break time reversal at the surface and open up a gap. So I've talked to experts and they tell me, well, I don't know. So I would love some kind of explanation like that, but